Solubility equilibrium. When a solute is added into a solvent, the solution is said to be saturated when no more solute dissolves in the solvent. Solute mixed with solvent to produce solution. This equation is reversible. Solution can become solvent and solute again. In a saturated solution, a dynamic equilibrium is achieved between the dissolved solute and the undissolved solute. At equilibrium, the rate of forward reaction that dissolves in the solute equals the rate of the reverse reaction of precipitation. So solute mixed with solvent to become solution, this rate is equal to the rate of solution becoming solvent and solute again. The solubility of a salt is the amount of solid that dissolves in a known value of saturated solution. The unit can be gram per liter or mole per liter. The symbol that we use for solubility is S. Solubility rules for common ionic compound. Soluble compounds or compound containing alkali metal ions and NH4. There is no exception for alkali metals ion and NH4+. NO3-, HCO3-, ClO3-, all these compounds are soluble with no exception. Chloride, bromide, iodide are soluble compound except when the silver Hg22+ or Pb2+ combined with any ClBr or I, the compound will be insoluble. Sulfate, soluble compound, but if it pairs with Sr2+, Ba2+, Pb2+, or Ca2+, the compound is insoluble. The insoluble compounds are carbonate, PO43-, CrO42-, and S2-, are insoluble compounds except when they are paired with lithium, sodium, potassium, or NH4+. If they are paired with these, the compound is soluble. Hydroxide compound is insoluble except when it pairs with alkali metal ion Ba2+, the compound will be soluble. Solubility-product constant. In terms of chemical equilibrium, a saturated solution is a solution in which undissolved solute and dissolved solute are in equilibrium. Ksp is a product of molar concentration of the ion involved in the equilibrium, each raised to the power of its stoichiometric coefficient in the equilibrium equation. The degree of solubility of a salt is shown by the value of Ksp. The higher the Ksp, the greater the solubility. Increase in temperature causes increase in solubility and Ksp. For example, solubility of PbF2 to becomes ion Pb2+ plus 2F-. So this Ksp product of the concentration of ion involved, so Pb2 plus times F2-, each raised to the power of its stoichiometric coefficient. Stoichiometric coefficient for Pb2 plus is 1, so power 1. This one is 2, so power 2. Solubility with symbol S versus solubility product constant Ksp. Solubility of a substance is a quantity that dissolves to form a saturated solution. It is often expressed as gram per liter or mole per liter. Solubility product constant Ksp is the equilibrium constant for equilibrium between ionic solid and its saturated solution. So this Ksp must be in equilibrium. For example, solubility calcium sulfate is found experimentally to be 0.67 gram per liter. Calculate the Ksp for calcium sulfate. given solubility S as 0.67, but the unit is gram per liter. We need to calculate KSP. KSP equal the concentration of the product over reactant. So concentration of the product must be in mole per liter, but here solubility in gram per liter. So we have to convert the solubility for gram per liter to mole per liter first by 0.67 divide 136.2 gram divide by the molar mass, gram per mole, and then the answer is 4.9 times 10 to the power of negative 3 mole per liter. So now our solubility is in unit mole per liter. We can substitute this into the KSP value to get the KSP value, because this concentration in here must be in mole per liter. So now construct the ice table. Calcium sulfate soluble to become Ca2 plus and SO4 2 minus. And then initially there are no product at all, 0. Change in concentration plus S, we use the symbol S for solubility. And then at equilibrium concentration is S for both Ca2 plus and SO4 2 minus. Substitute the value of S. S times S has become S squared, so 4.9 times 10 to the power of negative 3 square. The answer for KSP is 2.4 times 10 to the power of negative 5. So this is the KSP value. Predicting precipitation of ionic compound. Precipitate is the excess solid in saturated solution is an insoluble solid form and separate from the solution. This is precipitate. So KSP values can be used to make general prediction whether there's precipitate or not in that solution. To predict whether a precipitate will form, the ion product Q is compared with KSP. The Q has the same expression as KSP, but the concentration values are taken at any given time. KSP at equilibrium, Q at any time. Q versus KSP. Solubility product KSP. The concentration of ion involved in the equilibrium, each raised to the power of their coefficient in balance equation in a saturated solution. Ionic product Q, the product of concentration of ion involved, each raised to the power of their coefficients in the balanced chemical equation in solution at any concentration. KSP applicable only to saturated solution, but Q applicable to all types of solution of any concentration. KSP at constant temperature, its value is constant for a given solute, but for Q, the value keeps changing with concentration. Q versus KSP. When the value of Q is less than KSP, solution is unsaturated, no precipitate form. When the Q value is equal to KSP, this occurs when saturated solution form, the system is in equilibrium. When the value of Q is more than KSP, solution is supersaturated, precipitate will form until the ionic concentration product of the system equals the KSP until Q equal KSP. Saturated solution is a solution which contains the maximum possible amount of dissolved solute at equilibrium. Supersaturated solution, a solution containing a greater than equilibrium amount of solute, while unsaturated solution, a solution in which more solute can be dissolved at a given temperature, is called an unsaturated solution. A given solution that is saturated at a particular temperature may become unsaturated when the temperature is increased. So it depends on the temperature. For example, does a precipitate form when 0.1 liter of 0.3 molar calcium nitrate is mixed with 0.2 liter of 0.06 molar sodium fluoride. Given KSP of calcium fluoride 3.2 times 10 to the power of negative 11. So given KSP value for CaF2, the information given is CaNO32 and NAF. You need to mix this NAF and CaNO3 together first to get CaF2 and NaNO3. So here you get the equation of mixing these two together, get sodium nitrate and calcium fluoride. Now given the KSP for calcium fluoride, so we focus on calcium fluoride. In this solution, ion present is Ca2 plus and O3 minus, Na plus and F minus. Possible precipitate is only CaF2 because sodium nitrate, this one, sodium nitrate is soluble salt. So possible precipitate, we want to identify does a precipitate form. There will be no precipitate form for sodium nitrate because this is soluble salt. So possible precipitate is only CaF2. Okay, we focus on CaF2. So this is the equation for solubility of CaF2 becomes Ca2 plus and 2F minus 2 mole because here we have F2. The KSP expression equal concentration of the product Ca2 plus and F2 F minus square because this is 2 mole, so here is square. So given the value of KSP 3.2 times 10 to the power of negative 11. And then now we need to look at whether precipitate will form. So we need to know whether QSP is more than KSP or not, because if QSP more than KSP, precipitate will form. So we have the value of KSP, we want to identify the QSP. Now, in order to identify QSP, we need the concentration of Ca and F, Ca2 plus and F minus. But the Ca2 plus that we need is a Ca2 plus for CaF2, but we don't have that. We only have the number of mole of CaNO32. That number of mole we can get when we have the volume and the molarity of CaNO2. Now we calculate the number of mole of CaNO2 and then we get 0.03 mole. And then from here, this is the number of mole. When these two mix together, the volume of solution is not 0.1 or 0.2 liter. It's 0.1 plus 0.2. It's 0.3 liter. When these two mix together, the total volume is 0.3 liter. Now, we can get the new molarity of CaNO32 by taking this number of mole divided by that new volume. That is the new molarity of CaNO32 when it's mixed together with NaF. So this is the new molarity, 0.1. So from here, 0.1 molar, we ionize the CaNO32 to become Ca2 plus and 2NO3 minus. So here we ionize the salt, it becomes Ca2 plus. We want to know the Ca2 plus aqueous in order to get the Ca2 plus for CaF2. So when this is 1 mole, so 0.1 molar. So here Ca2 plus concentration is 0.1 molar. Now we already have the concentration of Ca2 plus. Next, we need to know the concentration of F minus. Because for KSP expression, to get QSP, we need F minus concentration. Now, F minus concentration we can get from NaF. First, calculate the number of mole of NaF, and then new volume, we'll get the new molarity of NaF, 0.04, and then the ionization of NaF is Na2 plus F minus. So 0.04 molar, 0.04 molar because 1 mole and 1 mole. And then, so the molarity is 0.04 molar for F minus. Now we already have the molarity of F minus, 0.04 molar, and we can calculate the QSP. QSP is Ca2 plus times F minus square, so we substitute in there the concentration we get, and we will get the QSP value 1.6 times 10 to the power of negative 4. Our KSP is 3.2 times 10 to the power of negative 11. KSP, this is KSP, QSP is bigger than KSP. So when QSP is bigger than KSP, the solution is supersaturated. When the solution is supersaturated, the CaF2 will precipitate until Q equal KSP. Common ion effect. Shift of equilibrium caused by addition or the presence of a compound having an ion in common with a dissolved substance. So this is shift of equilibrium by common ion effect. Presence of a common ion decreases solubility of slightly soluble ionic compound. For example, here we have PbCrO4 dissolved to become Pb2 plus aqueous and CrO4 2 minus aqueous. So this is PbCrO4. When we add Na2CrO4, so this is common ion. Na2CrO4 has common CrO4 ion as PbCrO4. The common ion is CrO4 2 minus. They have common ion, these two. When they have common ion, if you add Na2CrO4 in PbCrO4, means the concentration of CrO4 2 minus increase. If the concentration of CrO4 2 minus increase, the equilibrium shift to the left to make it equilibrium again. To make it the dynamic equilibrium achieved, the equilibrium position shift to the left. So this is the KSP value given 2.3 times 10 to the power of negative 13. When you add the compound that has common ion effect, it will shift the equilibrium. That is common ion effect. Effect of addition of common ion CrO4 2 minus cause the concentration of CrO4 2 minus increase. According to Le Chatelier principle, the presence of CrO4 2 minus ion causes equilibrium position to shift to the left to form more PbCrO4, because CrO4 2 minus react with Pb2 plus to form PbCrO4. Means the concentration of Pb2 plus will decrease here and PbCrO4 will increase. If the equilibrium position shifts to the left, it makes the solubility of PbCrO4 decrease, because for us to say PbCrO4 soluble, the solution will form Pb2 plus and CrO4 2 minus. But when the equilibrium shifts to the left, it makes PbCrO4 less soluble. So solubility of PbCrO4 decreases. For example, what is the molar solubility of AgBr in pure water given KSP is 7.7 times 10 to the power of negative 13? In pure water, initially in pure water, there is no AgBr at all. So initially, this is the solubility equation, AgBr to become Ag plus and Br minus. In pure water, 0 Ag plus, 0 Br minus. Initially, there's no Ag plus and Br minus in pure water. And then, there is concentration of Ag plus and Br minus, plus S, because one more. At equilibrium, there is S for Ag plus, S Br minus. There is a solubility amount. So KSP equal product concentration Ag plus times Br minus concentration. So KSP equal S square. We have the KSP value 7.7 times 10 to the power of negative 13 So you can get the S value is equal 8.8 times 10 to the power of negative 7 molar. So this is the molar solubility. S is the molar solubility of AgBr in pure water. Next, we want to know in sodium bromide. What is the molar solubility of AgBr in an AbR with concentration 0.01 molar? Initially, that is the concentration of Br, but no Ag, because in NaBr there is only Br minus, no Ag plus. Initially, Ag plus concentration 0, concentration Br minus 0.001 molar Br minus, because in NaBr we have Br. Change in concentration plus S, and then at equilibrium, Ag is S, Br minus is 0.001 plus S. Given Ksp, so we have this 7.7 times 10 to the power of negative 13 Ksp value. And Ag plus is S, Br minus is 0.001 plus S. But we assume that because this is negative 13, Ksp negative 13, assume S is extremely small. So 0.001 plus S is equal to 0.001. So we ignore S because S is very small. So S times 0.001, because our Br minus is 0.001, we ignore S, equal to 7.7 times 10 to the power of negative 13. We'll get the molar solubility S for in NaBr is 7.7 times 10 to the power of negative 10 molar. This is molar solubility of AgBr in sodium bromide. 7.7 times 10 to the power of negative 10. In pure water, we have 8.8 times 10 to the power of negative 7. So compare the solubility of AgBr in water and sodium bromide. If you compare, molar solubility of AgBr in water is greater than molar solubility of AgBr in sodium bromide. Thank you.